students, in today's topic we are going to learn about the thermodynamic principles of metallurgy. What is metallurgy? It is a science which deals with the extraction of metals to their pure state. This consists of three steps. First, concentration of the ore. Secondly, extraction of the crude metal. And thirdly, refining. In the second process, the extraction of the crude metal, two steps are followed. Firstly, the concentrated ore is converted into its metal oxide. Second step would be the reduction of the metal oxide to the crude metal. What is a reducing agent? A reducing agent is an element or a compound that can be oxidized easily. Importance of thermodynamic principles in metallurgy. Thermodynamic principles in metallurgy is important mainly for two reasons. To see if the reaction is feasible or not, that is, whether it is possible or not. Secondly, it is used for the selection of an appropriate reducing agent for economical extraction. Let us now see about the feasibility of a chemical reaction. When is a chemical reaction feasible? A chemical reaction is feasible when the reaction is spontaneous. Now, according to thermodynamics, we know that delta G is equal to delta H minus T delta S. Delta G stands for the change in the free energy. Delta H stands for the change in enthalpy. Delta S is called as the change in the entropy, and T stands for temperature. According to the above equation, delta G is equal to delta H minus T delta S. Delta G can have three different values. Delta G can be positive, can be 0, or it can be negative. When delta G is positive, it is non-spontaneous reaction. That is, it is not feasible. When delta G is at 0, then the equation remains at equilibrium. When delta G is negative, then the reaction is considered to be spontaneous, thereby feasible. Let us consider the reduction of a metal oxide. There are various metal oxides like Fe3O4, Mn3O4, TiO2, Fe2O3, Ag2O, ZnO, NiO, etc. So let us write the metal oxide in the equation as MxOy in the solid state. The metal oxide MxOy gets reduced as metal in the solid state and oxygen in the gaseous state. To balance equation 1, 2 atoms of oxygen on the product side and Y atoms of oxygen on the reactant side, we write it as 2 by Y MxOy. Y and Y gets cancelled, resulting in 2 atoms of oxygen on the reactant as well as on the product side. To balance M on the product side, it is multiplied by 2x by Y. This reaction can be reduced by using carbon. During this process, carbon can get oxidized to either carbon dioxide or carbon monoxide as per the equations 2 and 3. If carbon monoxide is used as a reducing agent, it gets oxidized to carbon dioxide. For determining the feasibility of reduction, the net delta G value for the coupled reaction, that is equation 1 plus 2 or 3 or 4, should be negative. If it is negative, reduction reaction is feasible. If more than one of the above coupled reaction has minus delta G values, then how to select a suitable reducing agent? In that case, the coupled reaction having the highest negative value for delta G is selected as a suitable reducing agent. Considering these thermodynamic principles, Ellingham constructed a graphical representation having temperature in the x-axis and standard free energy delta G naught in the y-axis. Delta G naught means change in the free energy at standard conditions like 25 degrees Celsius temperature and 1 atmospheric pressure. This graphical representation having the intercept delta H and the slope as delta S is known as Ellingham's diagram. Thus, the graphical representation of variation of standard Gibbs free energy of reaction for the formation of various metal oxides with temperature is called as Ellingham's diagram. Now let us see the various observations of Ellingham's diagrams. For most of the metal oxide formation, the slope is positive. Let us look into Ellingham's diagram for various metal oxides like the formation of Al2O3, MnO and ZnO. They all have positive slopes. A possible explanation for this is oxygen gas is consumed during the formation of metal oxides, which results in the decrease in randomness. Hence, delta S becomes negative and makes the term T delta S positive in the straight line equation y is equal to mx plus c. Secondly, carbon monoxide formation has a negative slope as can be seen from the Ellingham's diagram. This is because in this case delta S is positive as 2 moles of carbon monoxide gas is formed by the consumption of 1 mole of oxygen gas. It indicates carbon monoxide is more stable at higher temperature. Thirdly, as temperature increases, the metal oxide becomes unstable. As the temperature increases, delta G value for the formation of metal oxide becomes less negative and becomes 0 at a particular temperature. Below this temperature, delta G is negative and the oxide is stable, and above the temperature, delta G is positive, suggesting that metal oxides become less stable at higher temperatures and the decomposition becomes easier. Finally, there is a sudden change in the slope at a particular temperature for some metal oxides. This is due to phase transition, that is melting or evaporation. This can be observed in Ellingham's diagram for MgO, wherein we have a sudden change in the slope, as well as for HgO. Where is Ellingham's diagram applicable? Ellingham's diagram helps us to select a suitable reducing agent and an appropriate temperature range. The reduction of metal oxide to its metal can be considered in the following case. When the oxide of the element used for reduction is more stable, then the oxygen from the metal oxide combines with the elements used for reduction. One of the applications of Ellingham's diagram is that Ag2O and HgO decomposes at 600 and 700 Kelvin respectively, indicating that these oxides are unstable even at moderate temperatures and will decompose on heating even in the absence of a reducing agent. Secondly, Ellingham's diagram can predict the feasibility of the reduction of metal oxide of one metal by another. To remember in simple terms, the lower line present in the Ellingham's diagram reduces the upper line. This can be seen in the Ellingham's diagram. In the Ellingham's diagram, the formation of Al2O3 line lies lower to the formation of Cr2O3 line, meaning that Al2O3 is more stable than Cr2O3. Thus, Al aluminium can be used to reduce chromium and not vice versa. Thirdly, the carbon line cuts most of the metal oxide lines and thus can reduce all those metals at high temperatures. For example, let us look at the reduction of FeO by carbon. The lines of formation of FeO and CO intersects around 1000 Kelvin. So, below 1000 Kelvin, FeO line is present below the carbon line, implying that reduction by carbon below 1000 Kelvin is not feasible. Above 1000 Kelvin, FeO becomes unstable and the carbon line is present lower to the FeO line, implying that the reduction of FeO by carbon is thermodynamically feasible at this temperature range. Let us confirm this using free energy calculation. The free energy calculation confirms that the reduction is thermodynamically favored as shown by Ellingham's diagram. So, at 1500 Kelvin, the formation of FeO from Fe and oxygen has delta G value of minus 350 kilojoules per mole. On reversing the equation 5, that is decomposition of FeO, metal oxide to metal, the delta G1 value changes from minus 350 kilojoules per mole to plus 350 kilojoules per mole. In this reduction process, we use carbon as the reducing agent, which gets oxidized to carbon monoxide as per equation 6, having delta G value as minus 480 kilojoules per mole. On coupling reactions 6 and 7, we get a net delta G value of minus 130 kilojoules per mole for 2 atoms of iron as seen in equation 8. Thus, the standard free energy change for the reduction of 1 mole of FeO will be minus 130 kilojoules per mole divided by 2, which will be minus 65 kilojoules per mole, making this reaction thermodynamically feasible. Finally, let us look at the limitations of Ellingham's diagram. As Ellingham's diagram is based only on the thermodynamic consideration, it does not tell anything about the rate of the reaction involved. Secondly, it does not give any idea about the possibility of other reactions that might be taking place. Finally, Ellingham's diagram is based on the assumption that the reactants are in equilibrium with the products, which is not always true. I hope you have understood the basics of Ellingham's diagram, its observation, applications, and limitations. Thank you.